in the Physics and Applied Mathematics Unit, Indian Statistical Institute, Kolkata. So I don't need to introduce you the Indian Statistical Institute. It is one of the well-known institutes for statistics in the world. It has produced many renowned statisticians. It is difficult for me to read out all the popular names, but I read only one popular name, Professor Srinivas Varadhan. He won Nobel Prize a few years ago. And students, you know, Nobel Prize is the highest prize. It is almost equivalent to Nobel Prize in mathematics. And many other people have awarded many prestigious awards, so I don't want to go into the list. And as far as I understand, this Statistical Institute is maintaining a very good website. You can get all information from that website. And as far as Professor Dibakar Ghosh is concerned, he is one of the very active research scientists in nonlinear dynamics in India. In fact, he is collaborating with a couple of faculty members of our department for a long time. Our department has jointly produced several research papers in nonlinear dynamics with Professor Dibakar Ghosh. And as far as his academic background is concerned, Professor Dibakar Ghosh has completed PhD from Jodhpur University, Kolkata, and he joined as an assistant professor in Statistical Institute in 2012, and right now he is working as an associate professor. And upon visiting his homepage, I understand that he is supervising a large number of students. And nowadays it is very difficult to attract students to theoretical side, but he is managing that. And he is running a couple of research projects, including one from Indo-Russian War project. And as far as the research is concerned, Professor Dibakar is working on several frontier topics in nonlinear dynamics. To name a few, I spell chimeral states, extreme events, eco-evolutionary dynamics, and temporal networks. I said only few. And if you visit his website, you can learn more about him and his research work and other things. As far as today's talk is concerned, I requested him to talk about time-varying networks, which he kindly agreed. So with this short introduction, I request Professor Dibakar Ghosh to start his lecture. Okay. So students, you can, if you have any doubt, you can ask him at any time. Over to you, Professor Dibakar. No, we are not able to hear you.
Yes. Yeah. Thank you, Professor Synchronization, for your nice introduction on our institute. And so I am sharing my screen. Yeah, is it visible?
Yes, yes.
Just 1 minute. Just I have my video just for better presentation. Yeah, today my talk is on time-varying networks and some challenging issues which we have solved some problems, and there are many other issues which we can't do till now. I will discuss all this. What is the main problem for solving or handling these time-varying networks? So good morning to all of you. It is my great pleasure to speak today online lecture organized by Department of Nonlinear Dynamics, RUSA University. I am especially thankful to Professor Senthil Bhilan for the kind invitation and for choosing this topic on time-varying networks, which I am also always interested on this work. I have already a nice relationship with RUSA University for last few years with Professor Lakshmanan and also my friend Professor Muruganandam. I have already published a few papers with them, and most of the papers are on chimera states. But today we will not discuss on chimera states. In future, if we get any chance, we will discuss with you the chimera states. But today we will discuss on time-varying networks, which is an interesting research field nowadays. Before start my lecture, I would like to say something, just few words about my institute. Yeah, just I am open my institute web page from there. My institute website is www.isical.ac.in. This is a central government institute, and this is an institute of national importance. And this institute has many centers all over India. The main campus or headquarters at Kolkata, and other centers are Delhi, Bengaluru, Chennai, Northeast Center at Tezpur, and also recently founded one new campus, RCPO Center for Cryptography and Security. This is only for cryptology and security science. For student information, I want to just show their academic program, which is organized by ISI. Here, the main course is statistics and mathematics. So if you are interested on stat and math, then it is the best place in India for statistics and also for mathematics. For statistics, we have two bachelor courses. One is BStat, means Bachelor of Statistics. It is 3 years. It is mainly held at offered at Kolkata. And another one is Bachelor of Mathematics, this is BMath. This is also 3 years course. This is offered at Kolkata and Bengaluru, both center. Beside this, there is one, also these two courses are also master degree offered, MStat and MMath. And also another two subjects are important here, and one is quantitative economics. The Master of Science in Quantitative Economics. It is two centers, Kolkata and Delhi. And as I know, I'm not in economics background, but as I know from my institute that for economic course, this is the best institute in India. And also there are other courses, and MTech in Computer Science. It is one of the very prestigious course here, MTech in Computer Science. And there are also some diploma courses at Tezpur and Chennai and other courses. And my department is Physics and Applied Mathematics unit. It is a very small unit. In our unit, we have no regular courses like MSc in Mathematics or MSc in Physics. We have no courses. Mainly PhD work are done here. And beside this, of course, your project work or internship or summer vacation or MSc project also are available. The students, you can visit my our department website and go to the faculty members. You will see some faculty members. At present, we have 10 faculty members working in different fields, including cosmology, astrophysics, high energy physics, condensed matter physics, and quantum information theory. All are many fields are available here. For internship or your MSc project, one necessary document you have to, that course should be a regular course in your MSc course or in your BSc course. So if you are interested to apply here internship or any kind of project, you directly apply to the faculty members, and you will get reply hopefully, and you can do the project work with our faculty members. Before start my work, I just introduce some of the collaborators and my students who are working on time-bank networks. The first of all the students are my PhD students. At present, Bidesh and Somen are doing their postdoc at Israel, and Swarbendu is submitted his thesis, and Sayantan also submitted his thesis, and Gaurav and Said are working at PhD work. And other collaborators are, I am very thankful to them. I have learned many things with working with them. Professor Sudeshna Sinha, Urigen, Eric Bolt, Abhidesh Prasad, Monish Shimali, and lastly Stefano Bocaletti. Recently, we have written a review work on time-bank network with Stefano, and that accepted in physics report recently. The title of my talk is about time-bank network, and there are some challenging issues. So the first question, what is the importance of complex systems or complex network? As you know that many real systems can be modeled as networks, where the elements of the systems are nodes and the interaction between elements are edges. And even large set of systems can be modeled using dynamical processes on networks, which are in turn affected by the local dynamics of the nodes. Network thus present the backbone of many complex systems, and their theoretical and numerical analysis makes it possible to gain insight its numerous applications. As networks are omnipresent in many disciplines, including sociology, transportation, economics and finance, biology, and many physical systems. For this reason, the study on complex network has thus become a crucial component of modern scientific research. From the last 20 years, complex network theory has offered a powerful platform for the study of several distributed systems found in nature, and allowed us to better understand the intimate relationship between the connected topology and the emerging dynamics on the top of the nodes. Why we are interested in time-varying networks? What is the necessity of time-varying networks? Introduction. As more and more real systems find a suitable representation in terms of graph, basically in terms of network, it becomes necessary to design more and more sophisticated and realistic description of the connectivity pattern. In this context, there is a significant amount of recent work in physics and biology and social sciences pointing to the need of establishing time-varying nature in the connection among the system nodes. Initially, the study on complex network are based on a static connection. That is, the connection among the nodes are fixed in time. But very recently, different observation conclude that the connections may not be always static. They are time varying in nature. Today, in my talk, we will discuss some time varying features of the connection and their emerging dynamics. And there are some difficulties for analytical calculation of their collective states like synchronization. Since there are many master degree students here, just I briefly introduce just what is meant by chaos and what is meant by synchronization and what is the coupling topology, unidirectional bidirection, very briefly just for them. You know that the Lorentz system, perhaps you listen this word Lorentz systems, and for chaotic systems, we know that the deterministic system, nonlinear dynamic systems, chaos is one of the important features. For chaotic systems, just we see that all the trajectories are bounded or not. There is no periodic orbit exist or non-periodic aperiodic orbit. And the last point is important, the sensitive dependence on initial condition. For nonlinear system, these features will occur. For linear systems, if the linear systems may be sensitive dependence on initial condition, but the solution may not be bounded. For nonlinear system, these three features, if you observe, then we can say that the system is chaotic, and you have to further characterize the chaotic states by Lyapunov exponent. What is meant by sensitive dependence on initial condition? Just I have taken just Lorentz systems and fixed the parameter values at chaotic state. Just I have choose two different initial conditions, the blue lines for these initial conditions and red line for this initial condition. You can see that the initial condition for y and z are constant, just slightly disturb the initial condition of x at the order 10 to the minus 3. And you see that the upper picture, the initially they are almost close to each other, but after some times they are diverging to each other. But still, their attractor shows that the system is still bounded. Next, we come to the couple equation. We just couple two nonlinear systems. Then we study whether two systems are synchronously behavior or they oscillate synchronously or not. The synchronization first observed in 1665 by Christian Huygens, where two pendulums are oscillating or suspended through a common beam. After that, the synchronization phenomena is also observed in some natural phenomena by clapping in theater or fireplace. There are many examples you can get where the synchronization is occurred. Just I introduced just coupling, what is meant by coupling, and in general we have to consider two types of coupling. One is unidirectional, another one bidirectional. And also there are many types of synchronization occur, but today in our lecture we will concentrate on complete synchronization. Yeah. So this is suppose this is a sender and this is a receiver. So sender is a message to the receiver. For this, the driver or sender systems as it is in chaotic states, isolated dynamics, and the response systems, we have added this diffusion coupling plus epsilon x1 minus x2. If we change this coupling from 0 to non-zero, then after a critical value of coupling, we see that this lower bottom figure, that after critical value of epsilon, that is greater than 0.2 something, the two systems are synchronized, means the difference between x1 and minus x2, this tends to 0 as it tends to infinity. If we plot their x1, x2 manifold, that is we call this a synchronization manifold, that is x2 equal to x1. Another one coupling is bidirectional coupling. Just two oscillators are talking to each other. Just system 1 send a message to system 2 and system 2 also send a message to system 1. In this case also, after a critical value of the coupling strength, the two systems are synchronized and the corresponding synchronization manifold will be y equal to x line. And the time series of x1 x2 are overlapping, means as t tends to infinity, the value of x and y, x1 and x2 are converges. So this previous two slides was for two couple oscillator. Now we increase the number of nodes. That is, number of nodes will increase beyond 2. For that we just represent by a complex network. Network G is mathematically represented by a pair of two sets. One is V and another one is E. And V is the set of nodes and E is the set of edges. So this network may be undirected or directed, that is like unidirectional or bidirectional. We can say that the network is undirected if Vi and Bj, Vi-Bj pair means if Vi-Bj belongs to E, that means there exists a link from the node Vi to the node Vj. And if Vj, Vi also belongs to E, then we say that this is undirected, that is the connection is bidirectional, otherwise it is unidirectional. We represent the connectivity between n nodes because we are considering the number of nodes beyond 2 greater than 2. So we represent the whole connection by a matrix. That matrix we call adjacency matrix A. And the element of the adjacency matrix will be Aij equal to 1 if there is a link between ith node and jth node. Otherwise, it is 0. And for simple graph, since we are not considering any self loop in the node, so Aii equal to 0. So based on the degree of the network, we can divide the network as two parts. One is homogeneous and another one is heterogeneous. What is meant by homogeneous? If the node, every node has the same degree, identical degree, then we can say it's a homogeneous network. Or there are simple three well-known network. One is local network, that is each node is connected by its two nearest neighbor, and this non-local, each node is connected to by 2p number of nodes from each side, P number, and another one is globally, that is every node connected to all other nodes. And second type heterogeneous means you can see that the degree of V1 is 1 and degree of V2 is 3, because the V2 nodes connected with 3 nodes, V1, V4 and V3, and V3 is also connected to 2 nodes, V2 and V4. So V3 degree is 2. So every node has different degree. In this sense, we call that heterogeneous network. Now we come to our main topic, that is time-varying network. Up to now, we concentrate on those networks where the adjacency matrix remain invariant with respect to time. However, there are several instances where the networks are strongly affected by time. Such time-varying networks or time-dependent networks are pretty common in many real applications, from social networks, biological networks or communication networks, and spreading networks, also time-varying networks. The time-dependent graph topology are perhaps more significant in modeling several systems. For time-varying networks, we just similarly we can construct the underlying network as function of time. So this is a order pair of Vt and Et. So the number of nodes can be varied with respect to time, and their connectivity also changes. So if we change to both them, that is number of nodes and connection, then we cannot handle analytical part, or it is very difficult for changing to both of them. So for them, we just assume just Vt equal to V, the number of nodes is constant, and the number of links between the nodes vary with respect to time. We can divide the time-varying network based on the connectivity. So we can say that all the nodes are static. That is, the nodes are not moving in their physical space, or spatially they are fixed. And the connection between the nodes vary with respect to time. Another one is mobile nodes. In mobile nodes, there exist a number of examples in which mobile nodes interact only for certain time duration, those who are close proximity to the nodes. First, we will concentrate on time-varying network where the connectivity matrix, that is adjacency matrix, Aij, vary with respect to time. Here in the bottom, I give a schematic diagram from which you can understand what is meant by time-varying network. In this figure, one such occasional interaction among the network of 5 nodes for n times, and how the adjacency matrix vary with respect to time. At time t, there is only one connection between 1 and 4 nodes. And at time 2, the next time, the connectivity changes. Connectivity between 1 and 4 are disconnected, but new connection created between 2, 3, 5. In this way, the connectivity between the nodes are changes with respect to time. This is for another 10 nodes example at different times, T1 and T2 times. So one of the possible approach to study the analytical stability condition is the master stability function approach. The master emissive approach, we call this as emissive approach, analyze the stability of the synchronous state of primarily identically coupled oscillator. Initially, Pecora and Liu discovered this method for identically coupled oscillator, but later some researchers extend this theory for nearly identical oscillators. The stability condition for synchronization using the emissive approach in the coupled nearly identical oscillator can be extended for other type of coupling also. This approach assumes that all the coupled oscillators are identical and the synchronization manifold is invariant. What is meant by invariant? The existence condition for the synchronization will be maintained. That is, the coupling function of each link is same and should vanish after achieving the synchronization step.
Excuse me,
Yes,
Dibagan,
yes.
you want to take questions then and now and then, or you want to take the questions at the end of your talk? Because some people has raised their hand.
Just a minute.
Which one? For example, Professor Tamilmaran has raised a question, it seems. You want to take it now or a bit later?
I think after finishing my talk, I will answer all the questions.
Okay. So okay.
Okay.
Right.
With Anman, please excuse. Just write the network equation. Just for MSF calculation, just discuss first what is MSA approach for static network. Then I can say that what is the difficulty to apply this MSA approach for time-varying network. That's why I briefly introduce the MSA approach, what are doing by Rupe Kora. Just a network equation we can write in this form. Just without this part, coupling part, the xi dot equal to f of xi means all the nodes have identical oscillators. They have identically and their epsilon part and Lij is the zero-row sum Laplacian matrix. These Laplacian matrices are nothing but just D minus A. What is D is the degree matrix and A is the adjacency matrix. There is a relation between adjacency matrix and for the study of synchronization, just all the nodes are synchronized coherently. So we can say that xi equal to x0 for I equal to 1 to n. When complete synchronization occurs, all the oscillators evolve synchronously. Now we check whether this synchronization state is stable, locally stable or unstable. For that, what we usually do in linear stability analysis, just we perturb the synchronization manifold by a small amount delta xi. Then, if we linearize this network equation near this synchronization manifold, we can get the variational equation in this form. This variation just you can see the Laplacian matrix, and B is the matrix from which you can say the which variable of the oscillators are connected by which variable. The synchronous state is said to be stable, locally stable, if for any small perturbation delta xi, each oscillator asymptotically converges to the synchronization manifold. That is, xi tends to x0 as t tends to infinity, or you can say that delta xi tends to 0 as t tends to infinity. So basically these variational equations become a linear equations. But this equation contain two component, parallel component and transverse component. Just I am deriving what is parallel and transverse component. To analyze the stability of the synchronous solution, we should concentrate on the stability of the variation of delta xi, which are transverse to the synchronization manifold. Here the Laplacian matrix Lij matrix, L matrix is real value square matrix and also symmetric. So we know that every square matrix is unitarily diagonalizable by its basis of eigenvectors. So there exists a matrix P where P in which every column are orthonormal eigenvectors of L. Then we can apply to separate this parallel and transverse component. We apply Schur transformation. This Schur transformation in this form in terms of P. Then the above variational equation becomes in this form, where U is the diagonal matrix and the principal diagonal elements are the eigenvalues of the Laplacian matrix L. So in terms of eigenvalue, we can write the equivalent n uncoupled systems in this form. And since L is a connected matrix, so we know that every connected matrix or symmetry, real symmetry matrix, so one of the eigenvalue will be 0. So if we put I equal to 1, that is gamma 1 equal to 0, then this term will be vanished, and ultimately we'll get this variational equation. This is nothing the linearized equation of the synchronous dynamics x0 dot equal to f of x0. And for other value of I, for 2, 3 to n, we get the transverse equation of the variational part. And now we calculate the Lyapunov exponent from this variational equation, and the maximal Lyapunov exponent of the variational equation lambda max we can plot is a function of the coupling state epsilon. So in this way, we can say that the synchronized problem can be converted to a fixed point problem. And although this part is we have done, or we have done by others members, but this is semi-analytical calculation because we are deriving the variational equation or transverse component, then we can numerically solve the equation and to find lambda max. For time-varying network, Gij is the Laplacian matrix, and this Laplacian matrix vary with respect to time. So what is the problem we are facing here? For temporal network, the underlying Laplacian matrix changes with to time. Therefore, its eigenvalues and corresponding eigenvectors are also functions of time. So the span of the basis of eigenvectors changes whenever the Laplacian matrix changes with respect to time. So this first one is 0, and gamma 2 to gamma n all are time dependent, and corresponding eigenvectors also time dependent. However, to eliminate the parallel error component from the entire error dynamics, we should project the error component to a unique space. So for that we have used Schur transformation, and image shape cannot be applied directly in the case of a time-varying network. Then in 2006, Stefano and his group just tried to solve this problem for time-varying network. They write the variational equation similar to above in this form. The key point is to notice that this equation contains n variational equation j equal to 1 to n. And this equation we can convert to a static if this summation part is 0. When all eigenvectors are constant in time. So we can realize that two different ways. Namely, the first one is coupling matrix G, GT is a function of is a constant, and another one they can produce that they can say that this we can calculate the variational equations if the coupling matrix GT commute at every time with the initial matrix G0. If this condition hold, that is, if the matrix is commutative graph, then the process can be solved. But this is a limitation. Later, in 2006, Stilwell, Eric, and Robertson, they discussed a method for fast switching stability criteria. For fast switching indicate that the time scales of the network evolves is faster than the time scale of the couple oscillators. Then they propose a lemma. On this. They say that if the time average systems has an asymptotically stable synchronization manifold, then the time-varying network also possesses an asymptotically stable synchronous solution for sufficiently fast switching. They propose a method for fast switching. For slow switching, their theory does not work. So what we'll do now? We apply this existing method for fast switching criteria. We apply in our time-varying network. So Lijt is a time-varying network. We just replace this matrix by a time average matrix L bar using this lemma. So finally, using Schur transformation and using the unitary matrix P, the transverse error equation can be written in this form, where U2 are diagonal matrix, and we can replace this U2 by our eigenvectors, eigenvalues of the average systems. Now we next I'll introduce to another type of network, which is multi-layer network, and another one is multiplex network. What is multi-layer network? Just we consider in the previous discussion we are considering one network. Now we'll move to, by taking two networks, they are connected in this pattern or in this pattern. Just if we want to see that what is the effect of one network in another network. So for representation, we just use as a multi-layer network or multiplex network. Multiplex network is a special type of multi-layer network where the number of nodes in each layer should be identical, and there is a unique connection between each replica nodes. That is, if the first layer is 5 nodes and the second layer is also 5 nodes, there is two types of connection in this network. One is intra-layer network, inter-layer connection, and another one is inter-layer. Inter-layer means the connection between the nodes of two layers. The another one is just you can consider this one example of neural hypernetwork. There is two neurons are connected by electric coupling or chemical coupling, that is gap junction or synaptic coupling. So recently Federer discussed that the networks may be connected at the same time, that is two nodes are connected by two defined paths. If two nodes are connected by two defined paths, then we can say this network in terms of hypernetwork. Just you can consider the cities of India in one network. Cities of India are the nodes, and they are connected by road and also air. So there are two types of network: road network and air network. We can see the how one network affects the other networks in terms of hypernetwork. For the synchronization state, because we are considering only synchronization states, for multiplex network, two types of synchronization we can observe. The first one is intra-layer synchronization, means the nodes in each layer are synchronized, and the nodes in the bottom layer, they are also synchronized. That is, we get two solutions. For upper load or layer 1, get one synchronous solution x0t, and layer 2 we get y0t. And another one, inter-layer synchronization, which is basically the nodes, corresponding nodes in the replica nodes are synchronized, whether the nodes in each layer synchrony or not, but the replica nodes correspondingly they are synchronized. If two synchronizations occur simultaneously, then we get a one synchronization manifold in the whole network, and we say that this is globally synchrony. Now I just show you some example by taking different types of network connections, and we observe interlayer or interlayer synchronization. The first one is stochastic multiplex hypernetwork. We are considering hypernetworks means each node in the layer 1 are connected by more than two types of connectivity, and similarly the lower layer also connected by two types of connectivity. Then we can write the equation in this form. These very complicated equations, just consider on the schematic diagram. Just you can say the layer 1 contain two adjacency matrices. One is A1, A2, and layer 2 also contain two adjacent matrices A3 and A4. And their connection between the nodes are stochastically varied. That is, at each time, just we rewrite this P inter with probability, stochastic interlayer connections, and when P inter equal to 0 means two layers, there is no connection between the layers, two layers are disconnected, and P inter equal to 1 means complete multiplex network we observe. The condition, the next problem is, if we choose, just you see that there are 5 Laplacian matrix here, so you can say for a certain value of coupling strength, the two systems are synchronized or not. You have to check first whether this interlayer synchrony is invariant solution or not. We mathematically prove that these two, for this type of network, the invariant condition becomes Aij 1 alpha t equal to A 2 alpha for alpha equal to one number of tiers, number of connections. So this theorem says that the adjacent matrix of layer 1 and layer 2 should be identical. And second one is Bi1 equal to Bi2 means the network will be fully multiplex network, or the interlayer coupling function should be vanished after synchronization achievement. These two are existence condition for the occurrence of interlayer synchronization for this type of network. Next, we can apply this interlayer synchronization manifold, and using the master stability equations, we can write the variational equation in this form. And if we take one particular example of RUSA oscillators, then there are two types of interlayer connections, Lij1 and Lij2, and one interlayer connection this. And we see that just varying the epsilon 1 and epsilon 2, we get a synchronization states into this region. This blue region are the synchronization states. Next, for the calculus of MSF, just we face different problems. Just I can share with you. Just the variational equation in this form. These are very big equations. This is a 2D n-1 dimensional couple error equations. For simple case for KOT system, if we take 3-dimensional systems, so D equal to 3, and if we take 100 number of nodes, this dimension becomes 951. If you want to calculate the Lyapunov exponent and the maximum Lyapunov exponent of this variational equation, you have to orthogonalize, or you have to, for the calculation of Lyapunov exponent, you have to diagonalize 550, 594 into 594 dimensional matrix. So this is a very difficult job. Recently, Sorrentino in 2012 in GP paper, he just gave a one solution. He said that if all the time average Laplacians are symmetric and commutative with each other, then the error equation, this couple equation, can be decoupled. Decoupled into 2D dimensional of n-1 linear equations. Later we further extend this condition, and we prove that all the time average Laplacians are symmetric, and if one commute with all the others time average Laplacian, then we can decouple this whole equation into n-1 linear equations. So we can save time, because 2D dimensional means just 6-dimensional matrix you have to diagonalize, and here 594 order matrix you have to diagonalize. So we save much time using our theory. So multiplex network of hypernetwork we can consider as one Laplacian matrix as a eigenvalue 0 and another all the eigenvalue are A. Other Laplacian matrices are considered as arbitrary. You have to check whether all the matrices are commutative at every time or not. And just you can take example for the first one, just erosion random network with S joining probability P. We can get this condition eigenvalue 1, 0, and all the other eigenvalue are A. So for multilayer network, dimensionality reduction of the MSF done in one tier, and for more than one tier, one interlayer Laplacian matrix should commute with all other interlayer matrix and interlayer adjacent matrix also. Then we can decouple, or dimensional reduction process can be applicable for that case. Just I take another example of time varying multiplex network. Just we consider two networks in form of multiplex, and their simple one connectivity and each layer LIJ1 and LIJ2. For RUSA systems, we study here for inter-layer synchronization and inter-layer synchronization. Here the main message is, if we change this network by introducing a reordering frequency F, what will happen? Just we see that just for inter-layer synchronization, if we change the reordering frequency from slow to fast, then the range of synchronization regions will enhance and increase. For the inter-layer synchronization, they are in the left side critical points is slightly increased, by right hand side we get much larger region for synchronization, and we can also verify this by using MSF calculation. The third one example is enhancing synchrony due to reordering frequency. Just we are interested whether just we have take 5 layers connectivity matrix, and we are the layer 1, 2, and 3 and 4 are static. We are introducing just time varying connectivity in middle layer. What will happen? Then you see that just inter-layer synchronization for static layer, it is near about 4. But if we introduce time varying nature in the middle layer, we can get the time varying layer synchronized much earlier. That is, enhancing synchrony in the intra-layer synchronization is observed due to time varying nature in the middle layer. And we can analytically prove that if inter-layer synchronization occurred in one layer, then all the layers will be inter-layer synchronization simultaneously. In our recent work, we see that whether these are 5-layer networks, just 5-layer multiplex in the form of multiplex network, just we want to introduce 5 layers are identical initially. Then inter-layer synchronization will observe. Now we introduce a parameter mismatch in the layer 0. What will happen? If you introduce parameter mismatch in the layer 0, then we see that the layer -1 and 1, the symmetric position layers are inter-layer synchronization occurs, and layer -2 and +2, these two outer layers are also synchronized. That is in the form of relay connections, the relay inter-layer synchronization observed in this framework. For numerical simulation, just we got RUSA systems, and when delta omega means parameter mismatch is 0, all the 5 oscillators are identical, we choose the coupling strength where the synchronization not occur. So this is desynchrony. And if we introduce the parameter mismatch delta omega to 1 at omega parameter value, then we see that after certain times it is synchronized. So due to introduce the impurity in the center layer, the symmetric position layers are synchrony in interlayer. And one interesting why are this type of synchrony occur, then we observe that if we introduce mismatch in layer 0, then layer 0 and 1 or layer 0 and -1 are in lag synchrony. Basically, by introducing the parameter mismatch in the middle layer, the lag is created, which is the responsibility for enhancing synchrony or makes the synchrony. And here just 0 and 1 means just layer 1 and 0, they shows lag synchronization, but their amplitude not totally correlated, just phase lag synchronization, we can say that. In another word, just we can calculate, we can observe inter-layer synchronization in time varying multiplex hyper network. Here similarly, just we can observe just whether the invariant by existence condition of inter-layer synchronization occur or not. Just we get this type of condition. The adjacent matrix at each layer should be identical, or the inter-layer coupling function should be vanished. Another condition is the multiplex connectivity should be identical, should be complete or isolated. And another one is the inter-layer connection function should be 0, which is not possible. So you have to take this condition. In the previous calculation, I have just discussed with you just local stability of the interlayer or intra-layer synchronization. Recently, you have observed that global synchronization using Lyapunov function is also possible for this case. For this case, we have to consider just 4 assumptions. The first one is the individual dynamics should be Lipschitz function. Second one is the interlayer coupling function is linear. And third is interlayer coupling function is also linear. And interlayer Laplacian matrix corresponding to identity should be symmetric at every time. Then we can apply Lyapunov function method, and we can get the global stability condition in this form after a long calculation. Just for RUSA oscillators, if I put the Lipschitz constant m equal to this form, finally we get the global stability condition in this form. Just I want to point one thing here. Just the global synchronization critical value of eta is much larger than the local stability critical value eta. This is due to many things, because we are considering quadratic Lyapunov functions, or this critical value can be more significant or more accurate if we choose better Lyapunov functions in near future. This was done by one part where the nodes are spatially, they are fixed, they are not varying with time. Now we consider the time-wave network where the nodes are moving in physical space. Just I show you one example here. In the left side figure, the arrow means these are nodes or particle moving randomly in 2D plane. And the right hand side figure is the connectivity matrix. So that this node is connected with this or this or this or this something. The connectivity, we have considered that each node, just if we just consider the flocking birds, so you can see that one birds cannot see at a time all the birds. They can see in their surrounding neighborhood. So we can consider that the agents or nodes are moving with a vision range. Vision range means this node can interact with those nodes which are lying with a circular vision range of radius r. By this, if the particles are moving, the connectivity right hand side figure, connectivity changes with respect to time. Previously, Puneet just observed that the mobile oscillator can synchronize in 2D plane. Later, we have extended this theory for 3-dimensional mobile oscillators and also for multiplex network of mobile oscillators. The time-wave network can also be constructed based on their different methods. One of the method is threshold control approach. Just this is a network. Just what is connectivity matrix here? The Gij or Gji equal to -1 if the value of the chosen state variable of the nodes I and j exceed the threshold at time t. So this is a snapshots by taking few nodes. That is, the nodes which are above this threshold line r, they are connected, and which are below this threshold line, they are not connected. Using this condition, we can make the time-wave network from this threshold control approach, and we can study synchronization or amplitude rate, anything. Another one is interaction based on closedness. Suppose we have n number of nodes. We know that chaotic system is highly sensitive dependence on initial conditions, so their connectivity changes with respect to time. So I just move all the nodes on the attractor, and we just consider this type of, just every oscillator has a closed circle. The nodes which are belong to this circle, they are connected with those nodes, and other nodes will be disconnected. If we see that by changing the time, all the nodes finally come to coincide with one nodes, and the system is synchronized. By changing the time, the connectivity between the nodes are increases, and finally they close to 1. GCC value close to 1 means they are all connected. Recently we have just studied just time-based network using dynamic coupling and synchronization amplitude depth. We have observed that is the connectivity will be spatially dynamic interaction or temporal dynamic interaction. The connectivity will be changes based on their spatial position, and another one is for temporal dynamics means the connectivity will be on for certain time, 0 to tau dash, and the rest of the times they are disconnected, just on-off type of coupling. In this result, a first order phase transition behavior may change into a second order transition in spatial interaction solely depending on the initial condition. And the position abruptly first order like transition is completely non-existent in the case of temporal network. These two important features we observe in these two papers. And the second one, I want to introduce a new field, which is swarmulator, the swarming in multi-agent systems. I just show you some natural examples. The first one is flocking birds and school of fish and group of sheep and ant of colonies. This type of behavior we observe in nature. Just we want to model this, whether can we model this type of phenomena in terms of multi-agent systems or not. The swarmulators means swarming and oscillating. Both occur simultaneously. In the previous discussion, synchronization occurs in individual nodes or agents coordinate their timing synchronously, but they do not move through space. A complementary form of self-organization occurs among swarming insect or flocking birds or schooling fish, where the individual move through space, but without altering their internal states. But in swarmulator systems, phase dynamics and spatial dynamics are coupled to each other. Why the study of swarmulators are interesting? Because swarming and synchrony, they have some common property. Both involve large self-organizing group of individuals interacting according to simple rules, and second, both lie at the interaction of nonlinear dynamics and statistical physics. In the last few decades, these two fields are studied individually and separately, but remain disconnected. Studies of swarm focus on how animal moves while neglecting the dynamics of their internal states. On the other hand, studies of synchronization do the opposite. They focus on oscillators' internal dynamics, not on their motion. In the last few decades, however, I have already shown some results on mobile oscillators. Few studies of mobile oscillators motivated by application in robotics and some developmental biology have brought the two fields into contact. The oscillators are interacted if they come to their close proximity. With moving oscillators, one assumption has been done that oscillators' location affect their phase dynamics, but not conversely. Their motions have been modeled as a random walk without feedback from the oscillator space. In 2007, Tanaka and his collaborators proposed an early contribution to the modeling of swarmulators. They consider chemotactic oscillator, where the oscillator's consumptions of this chemical depends on their internal states, thereby completing the bidirectional phase-space coupling.
Excuse me, Dipagar,
Yes.
whether slides are moving? Are you talking? Are you talking this slide? Yeah.
Yeah, yes. Slides are not moving. Yeah.
Okay. Okay.
Yeah. And recently, Stuart and his colleagues proposed a mathematical model for formulators. I just briefly introduce what is the model proposed by Stuart. They examine the collective dynamics of formulator, which are mobile particle or agents with both phase and special degree of freedom, which gives them synchrony and swarming both at the same time. This the first equation is the spatial dynamics and second is the phase dynamics. And you can see that the phase dynamics and spatial dynamics are interconnected. The VI, xi is the spatial coordinate. It is 2-dimensional or 3-dimensional for n equal to 2 or 3. And VI is the individual agent's velocity. And I act is the spatial attraction function. And I repulsion is the spatially repulsion function. F act means influence of phase similarity on spatial attraction. And F repulsion is the similar for repulsion. And H is the phase interaction between the phases, and omega is the natural frequency, and G is the influence of spatial proximity on phase interactions. And for the study, they have considered these above functions in this form. And here J is a parameter which measure how the phase similarity influence spatial attractions. And they have chosen A equal to 1 and J 0 to 1, so that the attraction function is always positive. Recently, we have worked on this model, and we consider this just proposing the competitive interaction into the model. So every oscillator moves in 2D plane with a vision radius r, and the circular region is covered as an attractive range of visions. In a sense, they can feel the presence of nearby oscillators and couple their phases attractively. And outside the range of the visions, the connection to get coupled positivity is lost, and the coupling is repulsion. We are considering this type of coupling, and theoretically prove that the particle or the agents have no finite time collision between them, and also they maintain a minimum distance delta between the particles. Using numerical simulation, just last theorem gives the possibility of collisions among particles in finite time. So we introduce the to check the coherency among the particles, just introduce Coulomb order parameter, and swarming are also characterized by another parameter. This is S equal to S maximum of S plus and S minus. The swarmator organize themselves in space and adjust their phases with time. So by changing this epsilon r and j, we observe 3 different states. One is static asynchrony, another is active phase wave, and another one is splinted phase wave. In splinted phase wave, the agents or whole the multi-agent systems can be splitted into 4 or 5 of groups with the same phases. To distinguish this parameter space, we have introduced T and S. Based on these 2 parameters, we distinguish these 2 states. What is T? T is the number of T is the fraction of oscillators that execute at least one full circle in the space and phase after discarding the transition period. Just I show this 5 states by this video, this the upper for different value of j and k. In the upper part, their coherent state means all the oscillators form a single group and they will be fixed in state or static. In the right hand side column, these two states are active, that is splinted phase wave and active phase wave. You can see that this up to this there are 7 groups are connected, then these 2 groups may be merged to each other, and finally we'll get multi-split systems with defined phases. If we consider local attraction phase coupling, then we can say that static cluster synchrony we can observe here. Next, we discuss about the flocking in multi-agent systems. The definition of flocking is very well known by the basic model in 1995 PL paper, and the distance between the agents Dij is of course always greater than 0, and their phases are converges. That is theta I tends to theta j at t tends to infinity. The basic model just proposed this by these 2 equations. First one is spatial and second one is for periodic phase dynamics. And here theta t average direction of velocities of particle including I particle within the circle of radius are surrounding the given particle. And delta theta is the random number. This like a temperature like variables which uniformly distributed by -a to a interval. Now we modify this model also. That is, the Bishek model gives the orientation of each particle. That is, all the particles are on the same direction or not. But their swarming is not possible using this model. So you introduce Bishek model along with swarmators. Then we can, just 1 minute. We can, yeah. The upper row is the physical position of the particle, and the lower row is the connectivity matrix, connectivity changes with respect to time. From this figure, just we are changing the radius of the vision range R, 3.2 to 2.5. Then you can see that at the first column, these 2 groups are formed. Also, these states are transient. After sometimes they will be converged to each other and make a one group. And the second column, these 2 groups are almost separated, and the distance between them is greater than 2.8, so they are not connecting to each other. They are separating 2 different groups, but still they are moving with the groups and the nodes of one group not transferred to nodes of another group. So basically, finally, we just obtain 4 states: the 1 group and 2 group, 3 group, and 4 groups. I just almost end of my talk. So here I mentioned some major challenges which can be done in near future. Yet many questions remain open about the role of defined adaptive mechanism in the onset of macroscopic functional behavior. The first one is necessary and sufficient condition for complete synchronization or other states, chimera or amplitude death states. The necessary condition and sufficient condition in terms of coupling states, this not fully investigated, may be investigated in near futures. The second one, lack of experimental realization using circuit or any robot. The diverging synchronization patterns and death states emerging in time-varying networks. And finally, the third one, which is very interesting and challenging in network science, is that the study on the effect of higher order interactions. That is the to investigate the relationship between structure and dynamics in hypergraph or simplicial complexes. This is because the biology and to social sciences, the networks connectivity are not always pairwise. beyond pure interactions, that is, the interactions may be involved more than 2 nodes. This phenomena can be best represented by higher order interactions. And for higher order interactions, we can see these 3 problems: how higher order interactions manifest themselves in time-varying structure. Till now, there is no papers on time-varying networks on higher order interactions, how they change the functioning of such systems, and how can they be used for engineering or control the behavior of real-world networks. The conclusion of my talk is just I have introduced the structure of time-varying networks and briefly introduced the linear stability analysis only on immersive approach, and also global stability conditions and synchronization in defined time-varying multiplex hypernetworks, and synchronization of mobile oscillators and swarm systems. Thank you very much for your kind attention.
Yeah. Thank you for your interesting talk. Now, the session is open for questions.
Yes, please ask.
Can you?
Sir, first of all, thank you for a very nice and detailed presentation. I have one question, sir.
Yes.
Sir, what rules will the network, will the links follow while rewiring?
Yeah, we are. Can I answer this?
Yes, sir. That's my question.
Yeah, the network, we change the network by introducing a rewiring frequency. So at every time, we just take a probability that 2 nodes are connected by a probability P, and P equal to F into dt. F is the rewiring frequency and dt is the integration time step. So if we just consider dt equal to just 0.01, so the fast switching means you have to take F near to 100. Then every integration steps, the network will switching by this rewiring frequency. By way of introducing this rewiring frequency, which changes the network.
Oh, okay, sir. Thank you, sir.
Yes.
There are a couple of questions in the chat box. Can you?
Yes.
Those, yeah.
The first one is Srijita N. Sir, how can you classify the nonlinear PD into ellipse, hyperbola, and parabola? Is the same criteria for classification linear PD as applicable to nonlinear PD also? The first one is nonlinear PD. You can hopefully these are already available in textbooks, and of course there's another option. We can say that I have worked on some plasma models where the PD equation, only the PD equation, we can convert into ODE equation by Galerkin or Fourier transformation by taking 3 or 4 modes, and then we can apply the nonlinear ODE concept as well as, and otherwise you can there's some already some theory already developed. I don't know the exact theory on PD because I'm not working on PD never. Just I work PD on just converting the PD to OD and then apply the OD linear stability analysis. The second was Department of Non-Nonlinear. Everyone requested to Magir. The third one is Prashant Singh. Sir, I have a basic question, sir. In multi-layered systems, what does it mean they are synchronized as well as time varying? Yeah, for multi-layer networks, we discussed 2 types of synchronization. The first one is suppose 2 nodes we have. These n nodes and the another layer has n nodes. The n nodes, 2 layers, all the nodes in this upper layer are synchronized. All the nodes in the lower layer are also synchronized. This is one type of synchronization we call intra-layer synchronization. And second one is the nodes, 2 layers are not synchronized, but their replica are synchronized. When we introduce time-varying nature in multi-layer network, then the question is that you can see that there are very different possibilities for the connectivity. Interlayer, and if you consider hyper network, there's more than one type of interlayer connections. So the question is whether the synchronization state will be exist or not. That's why we are find some criteria for their synchronization conditions. And time-based nature, you can introduce the connectivity matrix, and synchronization will be the emerging states between the nodes on top of the between the edges on top of the nodes. Yeah. So I think this is your answer.
Doctor, this is Karthikeyan from Center for Nonlinear Systems.
Yes, Karthikeyan, say.
Yeah, I have a doubt in this formulators.
Yes.
Actually, we tried to work on such areas, but the problem is, have we been discussing any interplay between the position or the orientation of such oscillators, mobile oscillators?
Yeah, for orientation, just we have considered just. Do you want to know the numerical schemes or?
No, I'm just curious whether all these three interplays, the phase, interface, orientation, and the position have been.
Yes.
I was just curious on knowing that.
Yeah, these are said that the problem is very difficult. Yeah, not very simple, because you have to manipulate, you have to control many things.
Yes.
So for that, in our work, just we have considered basic model.
Okay.
And the position coordinate we take from Stochastic model.
Okay.
That is swarming. In basic model, the oscillators are moved in a group, but not swarming, not divided by 3 or 4 groups.
Okay.
That's why we introduce the swarmulators dynamics into this with their concept of basic model. And of course, we have to add some additive noise in the systems.
So to make the randomness.
Yes, random.
Thank you, Doctor. Thank you.
Yes. Thank you.
Hi, Dibakar. Can I have one question?
Yes, of course.
Very nice talk, Dibakar. Very good.
Yes, thank you.
So 2 points. One is you talked about enhancing synchrony by rewiring the middle layer.
Yes.
So what is the type of rewiring you do? Random rewiring, or is it based on any conditions?
No, just random rewiring. Just we introduce the real frequency f and vary the f, and we have checked whether for slow switching and fast switching 2 cases.
Okay.
For fast switching, our stability condition matches with fast switching, and numerically we have checked that whether slow switching this enhancing effect or not. Basically, in the previous all the works for enhancing synchrony, the people have either work on introduced by parameter mismatch in the local dynamics, or introduce the time delay coupling in the coupling functions. Then we say that whether the network connectivity can create this type of behavior enhancing or not.
Okay. Also, there was a counterintuitive case where you said by introducing a mismatch in the middle layer in the parameters, it is actually enhancing synchrony.
Yes.
But if the reason you said is for the delay, causing the delay, that means the detuning can be only in the frequencies. It cannot be in any other type of parameter. What do you think? The case you considered is a detuning in the frequency for the Rosler oscillator.
Yes.
So therefore, the next adjacent layers get a delay.
Yes.
But if it is in any other parameter, like any
other parameter, just I can remember one.
Okay.
The first one is enhancing synchrony in dynamical network.
Okay.
I have worked in 2012 in PRE paper. That in that paper we have taken 3 oscillators: Lorentz, Rosler, and McEgler systems.
I see.
For 3 oscillators, it works.
Okay.
And for Rosler, for Lorentz, maybe the R parameter 28, 25 to 30 in this range.
And also for these time varying networks, is there any way to ensure their commutability? Commutating or not?
No, we are relaxing that property. Just every time, otherwise every time you have to check whether the Laplacian matrix is commutative or not. We can remove this by recent theory, just introduced by Lupekora and these motor groups. And this is a simultaneous block radiation approach.
Mhm.
If the Laplacian matrices are not commutative, then we can decouple using simultaneous block diagonal approach.
Oh, okay. Still, even in non-commutating cases, you are saying something can be done.
Yes.
Ah, okay.
We got one result, and this in the last week we have published in archive.
I see. Great.
Yeah.
Okay. Thank you, Dibakar.
Yeah, thank you very much.
Bye.
Hi, Senthil.
Yeah.
Hi, Dibakar. Yeah.
Senthil Kumar from ISET.
Yes. I know my
Yeah,
friend.
Dibakar, this is Sandil. Yeah, so it's a nice and informative talk.
Yes.
So for this time varying network, you said that the frequency of switching should be very high, right?
Yes. For fast switching, yeah.
For synchronization, yeah, fast switching, the frequency should be high.
Yeah.
So does this should have any correlation or has any relation with the time scale of the system? It should be faster than the time scale of system,
of course.
or it may not.
Of course. The connectivity probability, if we consider P, then P equal to F into the dt. The dt is the time scale, that is integration time state for known dynamics, and F is the reorder frequency. But the synchronization is also occur for low switching or medium switching, but for support or ideal calculation, we have to take fast switching approach.
Okay, yeah. So because I expect that there should be some kind of correlation or relation between the time scale of the system and the switching in order to attain synchronization.
No, that relation is P equal to F into dt, just P is the reorder frequency probability.
Right. Okay, yeah. Thank you very much. Right. Okay, thanks. Thank you. Yeah.
I think there is a question in the chat box.
Yes, Prashant Singh.
Yeah.
Why number of domains were created on changing the parameters of a systems which were not connected? Why every component of the domain should be isolated by network by another domain of a particular? Why number of domains are created on changing the parameters of systems which are not connected? I don't understand this question, but which angle you? It is better if you talk.
He was our MSc student.
Yes.
Just now he has finished his.
Yes, no problem. The question is, no, we are changing the parameter where the.
Prashant, can you come? Can you speak now?
Sir, excuse me, sir.
Yes.
Yeah, you can speak.
I don't know. I'm understanding fully, but in one slide on changing the parameters, the particular domains were created. So I was asking that why every component of a particular domain should be isolated from the another domain. Is it possible that even they are isolated, there could be one component of one domain which is trying to get connected from the one component of another domain? Is it kind of partially isolation?
No. Just for complete synchronization, we are trying to see the collective behavior of the whole network. If we partially disconnect some nodes, they are not connected. They are not talking to the other nodes. They will not synchronize with them. Yeah, they should be separate. Separately, they will be studied.
Okay, sir.
Yeah. Basically, for complete synchronization, you have to maintain one criteria. The network should be connected. Means every nodes should be connected by either homogeneous network or heterogeneous network. What should be connected?
No, sir. I was talking for like there was a situation where the domains were created, like 4 to 5 domains, and
Yes.
Yes, sir. Yes.
Oh. No. Initially they are connected. But finally their emerging states are not connected. They are different states with different phase.
Yes, sir. Yes, sir. Even they are like isolated, but I was asking that.
They are isolated. They are moving separately.
Yes, sir. I was asking that is it possible that once they get isolated and we created a situation that only a particular component of one domain is trying to get connected by another domain of a company?
This may be possible by changing your master equation. You have to change.
Okay, sir. Thank you. Sir.
Thank you, Prashant.
So, are there any more questions? So, if not, So, yeah, any question? Any other question? No.
So no questions. I want to thanks all of you
Yeah,
for,
no,
your
no,
kind,
I
for,
wish
your,
you
for,
thank you.
for your kind attention to listen this long lecture.
Yeah, thank you very much, Dibakar, for giving a very interesting talk on time varying networks. I hope the students can understand at least what are the terminologies and what people are doing. Oh, thank you very much.
So students, for the students' information, if you have any questions, you can write a mail to me. I will give a reply.
Yeah, sure. If you have any questions, you can write to Professor Dibakar Ghosh by
Yes,
email.
of course.
Yeah.
Anytime you can mail.
Yeah.
Thank you.
Thank you. Thank you, Professor Ambiga, for attending.
Bye. Nice
Bye.
meeting you.
Nice to meet you.
Bye.
And see you